Imagine discovering that the simple act of looking at something fundamentally transforms the nature of that object, not through physical contact or any external force you can measure, but purely through the act of observation itself, as though reality exists in an undetermined state of pure possibility, until the precise moment your awareness collapses it into a single, definite outcome. In 1927, physicists conducting experiments with electrons made a discovery so profoundly disturbing that nearly a century later, scientists still debate its implications for the nature of existence. Particles behave as waves spreading across space when nobody observes them. But the instant measurement occurs, they snap into behaving as particles with definite positions. And this is not philosophical speculation or metaphorical language, but literal physical fact, confirmed through thousands of meticulously controlled experiments performed in laboratories across the globe using increasingly sophisticated technology. What makes this discovery truly unsettling is not merely that observation changes behavior at the quantum scale, but that the change happens instantaneously the moment observation begins, as though the universe itself responds to being watched by fundamentally restructuring the way matter exists, suggesting that what we call objective reality may not be a fixed independent substrate existing, whether anyone observes it or not, but rather a system of probabilities that crystallizes into definite states only when consciousness engages with it through the process we call measurement. This means that right now, as you read these words, every unobserved particle in the universe exists not in one definite state, but in a ghostly superposition of all possible states simultaneously, with reality branching out in countless directions, like an infinite tree of possibilities, and only through the act of observation do these possibilities collapse into the single timeline of events that we experience as concrete reality. The implications cascade far beyond physics laboratories because if matter truly behaves differently when observed versus unobserved at the fundamental quantum level that underlies all physical existence, then the boundary between observer and observed becomes not just blurred, but potentially meaningless, raising the disturbing question of whether anything possesses definite properties when nobody is looking, or whether the entire universe exists in an indeterminate probabilistic haze that snaps into focus only where consciousness directs its attention. Scientists initially believed this quantum strangeness would remain confined to the microscopic realm of atoms and electrons, irrelevant to the everyday world of tables and chairs and human bodies, but recent discoveries in quantum biology demonstrate that living organisms, including your own body, exploit quantum effects like superposition and entanglement for critical functions such as photosynthesis, bird navigation using Earth's magnetic field, and possibly even cognitive processes in the brain, suggesting that the strange quantum rules where observation creates reality may operate at every scale of existence, including the one you inhabit right now. The experiment that first revealed this reality-shattering truth is called the double-slit experiment, and despite its apparent simplicity, it remains one of the most elegant and simultaneously most disturbing demonstrations of how profoundly quantum mechanics violates our intuitions about how the universe should work. Physicists fire electrons one at a time through two narrow slits cut into a barrier with a detection screen positioned behind the barrier to record where each electron lands, and the critical variable they manipulate is whether or not they observe which specific slit each electron passes through on its journey from source to screen. When scientists do not observe which path the electron takes, leaving its trajectory unmonitored as it travels from the electron gun through the slits to the screen, the particles create an interference pattern of multiple bright and dark bands across the detection screen, exactly like the pattern you would see if waves of water passed through two openings and the resulting ripples overlapped with each other with peaks, reinforcing peaks to create bright bands and peaks canceling troughs to create dark bands. This interference pattern is mathematically impossible for particles traveling along definite trajectories because a particle must go through either the left slit or the right slit, and particles traveling through separate paths cannot interfere with each other the way waves can. Yet the electrons produce this unmistakable wave interference pattern when unobserved, proving that each individual electron somehow acts as a wave of probability passing through both slits simultaneously and interfering with itself. The truly mind-bending aspect emerges when physicists install a detector near one of the slits to determine which path each electron actually takes, not blocking the electron or interfering with its motion in any obvious physical way, simply observing and recording which slit it passes through, and at that precise moment the interference pattern vanishes completely as though it never existed, replaced by exactly what you would expect from particles. Two bright bands on the screen positioned directly behind each slit, with no interference effects whatsoever. The electron behaves as a wave spreading through both paths when unobserved, but collapses into behaving as a particle taking one definite path the instant observation occurs. And this is not an artifact of clumsy measurement disturbing the electron through crude physical interaction, because experimenters have refined the observation method to extraordinary levels of subtlety, using detectors that barely interact with the electron, reducing the measurement to the absolute minimum possible interaction. Yet the effect persists. Observation collapses the wave, turning probabilistic behavior into definite outcomes. Scientists have repeated this experiment not just with electrons but with photons, entire atoms, and even molecules composed of hundreds of atoms pushing the boundary between quantum and classical behavior to larger and larger scales, and every time the result remains identical, proving that the collapse from wave to particle upon observation is not limited to tiny subatomic particles, but represents a fundamental principle of how reality operates at levels that begin to approach everyday human scale. What transforms this from merely strange to philosophically catastrophic is that nothing about the observation process itself provides any classical explanation for why it should cause this dramatic change in behavior, because the detector measuring which slit the electron passes through does not physically block the electron, does not collide with it hard enough to knock it off course, does not emit radiation that pushes it in a different direction, but simply registers information about which path it took, and somehow that act of information gathering, that process of creating a record in the universe about which slit the electron went through, causes the electron to fundamentally transform from wave-like to particle-like behavior. This suggests that what matters is not physical disturbance but information itself, the fact that the universe now contains a record of which path was taken, and this record somehow forces the electron to have actually taken one definite path rather than existing in superposition of both paths simultaneously. The mathematics describing this process is called wave function collapse, where before measurement the electron exists in a quantum superposition described by a wave function that assigns probability amplitudes to all possible locations and states the electron might occupy, and this wave function evolves smoothly and deterministically according to the Schrödinger equation, spreading out in space and creating interference patterns when different parts overlap. But then at the moment of measurement, something completely different happens. The wave function instantaneously and irreversibly collapses to a single definite state, with the probability of each possible outcome determined by the amplitude of the wave function at that point in the space of possibilities. Nobody knows why measurement causes this collapse, what exactly qualifies as a measurement at the fundamental level, or at what precise moment the wave function stops evolving smoothly, according to the Schrödinger equation, and instead collapses discontinuously into a single outcome. And this puzzle is called the measurement problem in quantum mechanics, arguably the deepest unsolved question in modern physics despite decades of intense theoretical and experimental investigation. Some physicists propose that collapse occurs when a quantum system interacts with a macroscopic measuring device that has so many particles it effectively functions, classically amplifying the quantum event up to a scale where wave-like behavior becomes impossible, while others suggest that consciousness itself plays a role, arguing that the wave function collapses only when a conscious observer becomes aware of the measurement result, which would place mind at the center of physical reality in a way that most scientists find deeply uncomfortable. A third interpretation eliminates wave function collapse entirely, claiming that the wave function never collapses, but instead the universe splits into multiple parallel branches at each measurement, with every possible outcome realized in a different branch. So when you measure an electron going through a slit, the universe divides into one branch where it went left and another branch where it went right. And you simply find yourself in one branch experiencing one outcome, while another version of you in the parallel branch experiences the other outcome, meaning every quantum measurement multiplies the number of parallel universes in existence. These competing interpretations make identical predictions for every measurement you could possibly perform in a laboratory, which means there is currently no way to experimentally distinguish between them using quantum mechanics alone, leaving physicists in the philosophically awkward position of having a theory that makes spectacularly accurate predictions, yet offers multiple incompatible explanations for what the theory actually means about the nature of reality. But regardless of which interpretation eventually proves correct, if any of them can ever be proven correct, the experimental facts remain undeniable. Observation changes how matter behaves in ways that classical physics cannot explain. Particles exist in superposition of multiple states until measured, and the act of measurement forces a collapse into one definite state, creating what we experience as concrete reality from what was previously only probability. This is not speculative philosophy or abstract mathematics, but demonstrated physical fact, as real and verified as gravity or electromagnetism, yet far more strange in its implications because it suggests that the universe you inhabit does not exist in any definite state independent of observation, but rather materializes into specificity only where consciousness or measuring devices direct their attention, while everything else remains trapped in a ghostly, indeterminate condition of pure possibility. Most people assume quantum mechanics applies only to bizarre microscopic realms completely disconnected from everyday human experience, too small and strange to matter for the world of tables and chairs and human bodies operating at scales billions of times larger than individual atoms. But this assumption grows increasingly difficult to maintain, as scientists discover quantum effects operating in biological systems that evolved over billions of years to exploit the strange rules of quantum mechanics for survival advantages. Photosynthesis. The process by which plants convert sunlight into chemical energy that powers most life on Earth operates at nearly 100% efficiency, far higher than any solar panel humans have engineered. And researchers discovered this impossible efficiency comes from quantum superposition, allowing energy to simultaneously explore multiple pathways through the molecular machinery of the photosynthetic complex, finding the most efficient route as a wave of probability before collapsing into the optimal path that delivers energy to where it needs to go. Birds navigate using Earth's magnetic field with extraordinary precision, and experiments reveal they accomplish this feat through quantum entanglement in molecules in their eyes, where pairs of electrons become entangled in a quantum state sensitive to magnetic fields, giving birds the ability to literally see magnetic field lines as patterns overlaid on their visual perception of the world, a sense that humans lack entirely, but which depends fundamentally on quantum effects persisting in the warm, wet, chaotic environment of a living eyeball. Some neuroscientists speculate that your brain might use quantum processes for certain aspects of consciousness or decision-making, though this remains highly controversial and unproven. But if true, it would mean your thoughts and awareness literally participate in collapsing quantum wave functions, making you an active creator of reality rather than a passive observer recording pre-existing facts. The watched pot that never boils is often dismissed as purely psychological, a trick of perception, where paying attention to something makes time feel slower, but viewed through the lens of quantum mechanics it takes on deeper significance. Because if your observation genuinely affects quantum processes in the water molecules and air currents around the pot, perhaps through some mechanism related to the quantum Zeno effect where frequent measurement slows or freezes quantum evolution, then your attention might literally slow the process you are trying to observe. The quantum Zeno effect demonstrates that continuously measuring a quantum system can freeze it in place, preventing it from evolving to other states. like a quantum version of the ancient Greek paradox claiming that an arrow in flight can never reach its target, because at every instant it occupies a fixed position, and something occupying a fixed position cannot be moving, and experiments confirm that sufficiently rapid measurement of quantum systems can indeed prevent them from changing states, effectively stopping time for that system by forcing it to remain in its current configuration through the act of observation. If mere observation can transform an electron from a wave spreading through space into a particle occupying one definite location, and if continuous measurement can literally freeze a quantum system, preventing its evolution through time, then the philosophical implications extend far beyond physics into fundamental questions about the nature of reality, consciousness, and existence itself. Does anything possess definite properties when nobody observes it? Or does the universe exist as pure probability waiting for observation to crystallize it into actuality? Is reality something that exists independently of observers and would continue existing in essentially the same form if all conscious beings vanished, or is reality fundamentally a collaborative construction created by the measurement actions of all observers in the universe, constantly collapsing quantum possibilities into definite outcomes? Where exactly is the boundary between the quantum realm of superposition and probability and the classical realm of definite objects with specific properties, and what determines when a system becomes large enough or complex enough to lose its quantum behavior and start behaving classically? Part 2 explores these philosophical implications in depth, examines what modern physics tells us about the role of consciousness in creating reality, and reveals why this question remains among the most controversial and unsolved problems in science, with consequences that reach into the very meaning of existence, and whether the universe you think you inhabit has any objective reality at all, independent of your observation of it. The most controversial question in quantum mechanics interpretation centers on what exactly counts as an observation capable of collapsing the wave function, whether this collapse requires the presence of a conscious observer or suffices with any physical interaction involving a macroscopic measuring device, and whether the answer to this question places consciousness at the foundation of physical reality or relegates it to an irrelevant byproduct of brain chemistry. Physicist Eugene Wigner proposed that consciousness plays a fundamental role in quantum measurement, arguing that the wave function cannot collapse through interaction with an unconscious measuring device because the device itself must be described quantum mechanically, and therefore also exists in superposition until a conscious being observes the device is readout, which would mean that without consciousness nothing ever collapses, and the entire universe remains in an ever-expanding superposition of all possible configurations. This leads to Wigner's friend paradox, where one observer inside an isolated laboratory performs a quantum measurement and sees a definite result experiencing the collapse of the wave function to one specific outcome, while an external observer who does not know this result still must describe the entire system, including the first observer as existing in superposition of all possible measurement outcomes, creating a logical contradiction if both observers are real and conscious, because reality cannot simultaneously be collapsed for one observer and uncollapsed for another, without introducing observer-dependent realities that contradict the assumption of a single objective universe. Most contemporary physicists reject the idea that consciousness is necessary for wave function, collapse preferring the decoherence interpretation, where interaction with the surrounding environment creates effective collapse through entanglement of the system with the vast number of degrees of freedom in the environment, causing quantum coherence to leak away into the environment so rapidly that superposition becomes undetectable, even though technically the wave function of the system plus environment continues evolving according to the Schrödinger equation without any true collapse. Decoherence explains why we never observe macroscopic objects like cats or measuring devices in quantum superposition in everyday life, because any object larger than a few molecules interacts so strongly with air molecules, photons, and countless other environmental particles that its quantum coherence disappears in fractions of a second, forcing it to behave classically from any practical observational standpoint, even if, fundamentally, it remains quantum. However, decoherence does not solve the measurement problem at a fundamental level, because while it explains why we do not see macroscopic superpositions and why the world appears classical, it does not explain why any particular outcome occurs in each individual measurement rather than the system remaining in superposition of all outcomes entangled with the environment, which means the question of what causes definite results to manifest remains unanswered by decoherence alone. This unresolved status of the measurement problem suggests that perhaps consciousness does play a role we do not yet understand, not because consciousness violates physical laws, but because consciousness might be a physical phenomenon intimately connected to the information processing and integration that occurs during quantum measurement. Philosopher David Chalmers argues that if matter behaves differently depending on whether it is observed, this implies that observation, information, or experience might be fundamental aspects of reality on par with matter and energy, woven into the basic fabric of physics rather than emerging accidentally from complex arrangements of unconscious particles. The philosophical position called panpsychism, traditionally dismissed as mystical nonsense by scientists, gains unexpected support from quantum mechanics if observation truly changes reality. Because if information and observation are fundamental, then perhaps some primitive form of experience or proto-consciousness exists at all levels of physical reality. Not that electrons possess human-like awareness, but that the universe contains experiential aspects at its foundation, rather than consisting purely of unconscious matter following blind mechanical laws. The Copenhagen interpretation of quantum mechanics formulated by Niels Bohr and Werner Heisenberg in the 1920s and still taught as the standard interpretation in most physics courses, asserts that the wave function represents a complete description of a quantum system and collapses irreversibly upon measurement into one of the possible outcomes according to probabilities given by the wave function. Is amplitudes, but offers no mechanism explaining why or how this collapse occurs, simply postulating it as a fundamental process that happens when quantum systems interact with classical measuring devices. This interpretation divides the universe into quantum systems that obey the Schrödinger equation and classical measuring devices that cause collapse, but never clearly defines where the boundary between quantum and classical lies, leaving physicists in the awkward position of having a theory that works perfectly for making predictions, but cannot explain what actually happens during measurement or even precisely define what constitutes a measurement. Many worlds interpretation proposed by Hugh Everett in 1957 eliminates wave function collapse entirely, instead claiming that all possible outcomes of every quantum measurement occur simultaneously but in different branches of a constantly splitting universe. So, when you measure whether an electron went through the left or right slit, the universe divides into one branch where it went left and another where it went right, and you simply find yourself in one branch experiencing one outcome, while another version of you in the parallel branch experiences the alternative outcome, neither version aware of the other's existence. From the many worlds perspective, observation does not collapse the wave function, but rather entangles the observer with the measured system, creating correlation between the system is state and the observer is memory state, such that in each branch of the universe the observer sees one definite result corresponding to that branch, even though the universe as a whole remains in superposition of all possible outcomes with no collapse ever occurring. This interpretation is mathematically elegant because it requires only the Schrödinger equation without any additional collapse postulate preserving quantum mechanics in its purest form, but it is ontologically extravagant because it postulates the existence of an astronomical number of parallel universes constantly branching with every quantum event, creating countless copies of you, experiencing every possible outcome of every quantum measurement occurring in your body and environment, most of which differ from your experience only microscopically, but some of which diverge radically when quantum events influence macroscopic outcomes. Both Copenhagen and many worlds interpretations agree perfectly with all empirical data and make identical predictions for any measurable quantities, which makes it impossible to experimentally distinguish between them. Using quantum mechanics alone, reducing the choice between them to philosophical preferences about the nature of reality, whether we should prefer theories that minimize ontological commitments even if they require unexplained physical processes like collapse, or theories that preserve mathematical elegance, even if they multiply entities beyond anything we can observe. Regardless of interpretation, the fact remains that observation radically changes how we must describe a system, transforming it from probabilistic superposition to definite outcome in a way that classical physics cannot accommodate, and this transformation has practical consequences extending far beyond philosophical debates into technologies that exploit quantum mechanics. Quantum computers harness the principle of superposition to perform parallel computations existing in multiple computational states simultaneously until measurement of the final result, demonstrating that quantum effects are not merely theoretical curiosities but can be technologically exploited to solve problems that would take classical computers longer than the age of the universe. The development of quantum computing proves that maintaining quantum superposition in carefully controlled systems allows information processing fundamentally different from classical computation, with quantum bits or qubits existing in superposition of 0 and 1 simultaneously, performing calculations on all possible input combinations at once before observation collapses the superposition to reveal the answer, a process that would be impossible if observation did not genuinely change the state of the system from superposed to definite. In quantum biology, researchers discovered that photosynthesis achieves its remarkable near-perfect efficiency through quantum superposition, where energy absorbed from sunlight exists in superposition of multiple pathways through the photosynthetic complex simultaneously, allowing the energy to explore all routes at once as a probability wave and naturally flow along the most efficient path to where it needs to go, collapsing into that optimal route upon arrival. Birds navigate using Earth's magnetic field through quantum entanglement in specialized molecules in their retinas, where pairs of electrons become entangled in quantum states sensitive to magnetic field orientation, and this entanglement persists long enough in the warm, chaotic environment of a living cell to provide navigational information, proving that quantum coherence can survive in biological systems at room temperature for functionally relevant timescales. These discoveries demonstrate that life evolved to exploit quantum mechanics, suggesting that quantum effects including superposition and observer-dependent collapse are not isolated laboratory phenomena, but active participants in biological processes that have been shaped by evolution over billions of years to function optimally within the strange rules of quantum reality. If quantum processes occur in biological systems, including potentially in your brain, as some theories of consciousness propose, though this remains highly speculative and controversial, then your thoughts and awareness might literally participate in collapsing quantum wave functions within neural structures, making you an active creator of reality at the quantum level, rather than a passive observer recording pre-existing facts. The idea that consciousness could be fundamentally quantum in nature faces significant skepticism from neuroscientists who point out that brains are warm, wet, noisy environments where quantum coherence should decay far too quickly to be functionally relevant. But recent evidence that quantum effects persist in biological systems under similar conditions suggests this objection may be less decisive than previously thought. Whether or not consciousness involves quantum processes, the philosophical implication remains profound. Reality does not exist as a fixed objective entity independent of observers, but rather represents a dynamic process where potential possibilities collapse into actual outcomes through interactions that involve measurement or observation. And each measurement by each observer contributes to the construction of what we collectively call objective reality, even though at the fundamental level, reality consists of probability waves that only materialize into definite states when forced to do so by the act of observation. The double-slit experiment proves beyond doubt that observation changes matter at the fundamental level. The measurement problem in quantum mechanics remains unsolved nearly a century after the theory's formulation, and debates about consciousness's role in wave function collapse continue among physicists and philosophers without reaching consensus. But regardless of which interpretation ultimately proves correct, if any can ever be definitively proven, the empirical fact stands undeniable. Your observation alters reality in ways classical physics cannot explain, and this is not metaphor or exaggeration, but literal description of how the universe operates at the most fundamental level we can measure. Perhaps the next time you look at something you should consider that the very act of your observation may collapse the wave function of that object from an indefinite state of superposition into the definite reality you perceive, and that without your observation, the object might exist only as a cloud of probabilities spreading through the space of possibilities, never actualizing into any particular configuration until the moment awareness engages with it through measurement. Reality is not what it appears to be, presenting itself as a solid objective world existing independently whether anyone observes it or not. But quantum mechanics proves with every experiment that this appearance deceives us, showing instead a universe where observation creates reality, where consciousness, or at minimum measurement, plays a constitutive role in determining what exists, and where the boundary between observer and observed dissolves into a participatory process where the act of looking makes things real. The implications extend into every aspect of how we understand existence, from the nature of time and causation to the possibility of free will and the meaning of consciousness itself, because if the universe exists in superposition until observation collapses it into definite states, then the past itself might not be fixed but rather crystallizes into a specific history only when observed. As Wheeler's delayed choice experiment suggests by showing that decisions made in the present can retroactively determine which path a photon took in the past. Your memories of yesterday, your records of history, your confidence that events happened in one particular way rather than another, all of this might represent not an objective recording of fixed facts, but rather a continuous process of collapse, where observation in the present creates a definite past from what was previously only probability, meaning history itself is not what happened, but what we observe to have happened when we look backward through time. This suggests a universe far stranger than the mechanical clockwork of classical physics, or even the curved space-time of relativity. A universe where reality emerges from the interaction between possibility and observation, where nothing is real until measured, where consciousness or measurement or information processing plays a fundamental role in creation itself, making every observer a participant in the ongoing construction of existence, rather than a passive witness to pre-existing objective fact, and where the answer to the question of what reality is when nobody observes it may be that reality simply is not remaining forever in the realm of unactualized potential until the light of awareness brings it into being.
Он махал руками, кричал до хрипоты, разжигал костер за костром. Вертолет пролетел в 200 метрах и не заметил его. Через 3 дня его нашли мертвым в 500 метрах от лагеря спасателей. Он был так близко, но остался невидимым. В постапокалипсисе недостаточно выжить. Нужно, чтобы тебя нашли. Ты можешь иметь запасы, укрытие, оружие. Но если не умеешь подать сигнал, умрешь в метрах от спасения. Сигнализация — это граница между жизнью и забвением. Правило 3. Запомни навсегда. 3 любых повторяющихся сигнала означают SOS. 3 костра в треугольнике. 3 свистка подряд. 3 вспышки света. 3 столба дыма. Это универсальный код бедствия, который понимают все спасатели на планете. 1 сигнал — случайность. 2 — совпадение. 3 — крик о помощи. Сигнальное зеркало — твое оружие дальнего действия. Обычное зеркало размером с ладонь видно на 15-20 километров в ясную погоду. Вертолет, самолет, наблюдатель на вышке — все увидит солнечную вспышку раньше, чем костер или дым. Техника проста. Прицеливайся через отверстие в центре. Направляй отражение на цель. Делай 3 короткие вспышки. Пауза. Повторяй. Нет зеркала? Используй начищенную консервную банку, отполированный металл, экран смартфона, CD-диск. Любая отражающая поверхность превращается в маяк. Дымовые сигналы работают днем, когда зеркало бесполезно в пасмурную погоду. Но цвет дыма решает все. Белый дым добавь в костер сырую траву, зеленые ветки, мох. Он поднимается столбом и виден издалека на фоне темного леса. Черный дым, жги резину, масло, пластик, автомобильные покрышки. Он создает плотную черную колонну, видную на десятки километров. Контраст. Твой союзник. Белый дым на фоне темных деревьев, черный дым на фоне светлого неба. 3 источника дыма в линию или треугольник – сигнал бедствия. Наземные знаки спасают, когда поисковая авиация облетает территорию. Выкладывай огромные символы из камней, бревен, вырытых траншей. Минимальный размер знака – 3 метра в длину, чтобы его увидели с высоты. Международные символы. X – требуется помощь, F – нужна вода и еда, 2 – нужны медикаменты, треугольник – безопасное место для посадки, SOS – экстренная помощь. Делай знаки контрастными. Светлые камни на темной земле, темные бревна на светлом песке. Размещай на открытых пространствах. Поляны, берега рек, плоские крыши. Звуковые сигналы пробивают туман, ночь и густой лес, где визуальные бесполезны. Свисток слышен на 1-2 километра. Человеческий голос только на 500 метров, и ты быстро сорвешь связки. 3 коротких свистка, пауза. Повторяй каждые 10 минут. Береги силы, не трать энергию на крик. Нет свистка. Стучи металлом о металл, бей в пустую канистру. Используй автомобильный клаксон короткими сериями. Звук должен быть резким, отличным от природного фона. Ночная сигнализация требует света. Костер на возвышенности виден на километры. Огонь притягивает взгляд в темноте. Фонарик, направленный в небо, делай 3 вспышки. Пауза. Повторяй. Светоотражающие элементы развешивай на деревьях вокруг лагеря. Они отразят свет прожекторов спасательного вертолета. Импровизируй. Фольга, куски металла, зеркала, светлая ткань на высоких ветках. Создавай маяк из нескольких костров в разных точках. Цветовой контраст работает постоянно, даже когда ты спишь. Яркие цвета на фоне природы кричат: «Здесь человек». Оранжевый, красный, желтый – лучшие цвета для сигнализации. Разложи яркую одежду на открытом месте. Натяни между деревьями. Положи на крышу убежище. Спасательный жилет, палатка, тент, даже яркий рюкзак. Все работает как пассивный сигнал 24 часа в сутки. Тайминг решает все. Самолеты летят по маршрутам в определенное время, обычно утром и вечером. Поисковые операции активны в светлое время суток, когда видимость максимальна. Готовь сигнальные средства заранее. Дрова для костра сложены, зеркало под рукой, свисток на шее. Услышал звук мотора? Действуй немедленно. У тебя есть секунды, не минуты. Критические ошибки убивают шанс на спасение. Костер под густыми деревьями не виден сверху. Дым рассеивается в кронах. Слабый дым теряется в тумане. Делай плотный густой столб. Сигналы в низине не видны издалека. Поднимайся на высоту. 1 сигнал воспринимают как случайность. Делай 3. Беспорядочное махание руками путают с обычным движением. Делай преувеличенные, медленные жесты над головой. Самодельные устройства работают не хуже профессиональных. Зеркало из осколка стекла, обернутого тканью. Сигнальный флаг из яркой одежды на длинной палке. Дымовая шашка из консервной банки, набитой дымящимся материалом. Световой отражатель из алюминиевой фольги. Звуковой сигнал из пустой канистры и палки. Изобретательность компенсирует отсутствие снаряжения. Так что пока другие машут руками и остаются невидимыми, ты применяешь правило 3. Используешь зеркало на 20 километров, создаешь контрастный дым, выкладываешь знаки на земле и превращаешь каждый сигнал в крик о спасении, который невозможно не заметить.